The power from the sun comes from combining small atoms to produce larger ones. It is a nuclear reaction known as fusion. A minute fraction of the energy given off is beamed down to Earth, where it powers the wind, drives the water cycle, and gives the energy needed for life on Earth. Beneath the Earth's surface is a second form of nuclear energy. Large atoms decay, giving off alpha and beta particles, producing heat we can use for geothermal power. Fusion and decay are the two natural nuclear energies. A third form is fission. Radioactive decay is covered in our nuclear physics video. Here we are going to look at fusion and fission. We'll look first at fission. The first use, or misuse of fission, was as a weapon. But unlike a bomb, the fission reaction in a power station is controlled, so that energy is given off only on demand. Nuclear fission means the splitting of a nucleus into two smaller parts. The nucleus is made up of neutrons that are neutral and protons that are positive. The protons repel each other. However, balancing this is a very short-range nuclear force. This force is produced by exchange of particles called gluons or pions. This exchange generates a force that binds the nucleons together. If an extra neutron is captured, some nuclei become unstable. As it wobbles and distorts, the nuclear force gluing the nucleus is acting over a smaller area. It can no longer counteract the electrostatic repulsion of the protons. So, the nucleus splits in two, giving off 3 neutrons and energy. This is a chart of stable nuclei. Uranium has a very high proportion of neutrons to keep the nucleus together. When it fissions, the uranium nucleus can split into any one of 40 different pairs of nuclei. However, in this region, the neutron-proton ratio needed for stability is much smaller. The fission fragments have too many neutrons for stability. The excess neutrons will emit beta particles turning into protons, thus increasing the atomic number of the fission products by 1. This is radioactive decay, not fission. The beta radiation from the fission fragments can be seen as a Cherenkov glow. These are spent uranium fuel rods being removed from a reactor and stored underwater. The beta particles shoot out, approaching the speed of light in vacuum. However, this is faster than the speed of light in water, and this glow is the result. It is an electromagnetic shock wave, similar to an aircraft breaking the sound barrier. It takes 1 neutron to cause fission, but this fission reaction gives off energy and 3 more neutrons. If these neutrons hit other nuclei, they too will cause new fissions. This is a chain reaction. If it happens quickly and out of control, it is an atomic bomb. After fission, a neutron is traveling very fast and will pass right through a nucleus. It can only be captured if it is traveling slow enough. If the pieces of uranium or plutonium are small, most of the neutrons will escape or be absorbed by the abundant uranium-238. If either of these happen, there will be no fission. As the pieces are brought together, more neutrons will be captured by uranium-235 nuclei, and this will cause fission. The smallest possible mass at which a chain reaction will occur is called its critical mass. For uranium-235, this is 15 kilograms, about the size of a grapefruit. If the uranium is kept at the critical mass and the neutrons are controlled by absorbing the excess, power can be generated in safety. The main components of a thermal fission reactor are a core of fuel, uranium, plutonium, or thorium, moderators to slow down neutrons to the right speed, usually water, but sometimes graphite, control rods to soak up extra neutrons, coolant, usually water, but sometimes a gas, any radiation shields to protect people and equipment. Uranium is the most usual fuel. It has 3 naturally occurring isotopes: uranium-238, uranium-235, and uranium-234. In a uranium-fueled reactor, the only isotope that will work is uranium-235. However, it is rare. The fuel for reactors can be used in various forms. In this case, uranium oxide is being pressed into ceramic fuel pellets. Some reactors use uranium metal, but it has a low melting point. This can be raised by using uranium carbide. The pellets are placed inside tubes to become fuel rods and then bundles. Some specialized reactors use plutonium as the fuel. The Japanese are going this route. In this reactor, water is being used as a moderator to slow down the neutrons so they can cause fission. The hydrogen in the water is similar in mass to a neutron, so a collision tends to transfer momentum to the hydrogen. However, the hydrogen in the water will absorb neutrons to become deuterium. If heavy water is used, that is, water made with deuterium, uranium can be used without enrichment because no neutrons are lost. As the neutrons slow down in the water, they heat it and boil it off. The fission reaction is controlled by controlling the number of neutrons. Boron or cadmium control rods capture neutrons depending on how far they are inserted. At the first sign of any emergency, control rods are immediately put in place. In the case of a boiling water reactor, the moderator is water, which is allowed to boil off as steam. It is the steam which drives the turbines and generates power. In a high-pressure water reactor, the water is kept under a pressure of 2,000 pounds per square inch and not allowed to evaporate. Steam is generated in a secondary circuit, and this drives the turbines. Escape of radioactivity is less likely this way. If carbon in the form of graphite is used as the moderator, the coolant no longer needs to be water. A gas such as carbon dioxide or helium can be used. It will be efficient because a higher temperature can be used. Another coolant is molten sodium. This is used in fast breeder reactors that use plutonium as the fuel. One of the worst things that could happen to a nuclear reactor is a loss of coolant. In this Canadian CANDU reactor, the core is supplied with 2 water supplies. If one of these bursts, steam would escape into the pressurized building. The buildings in Canadian power stations are designed in pairs. From here, the steam would go to the next pressurized building and be condensed by a shower of water. The design varies in different countries, but the principle is the same. All reactors have large supplies of makeup coolant, which can be brought in case of an accident. There are two kinds of radiation shields. Firstly, there is a shield around the inside walls of a reactor to protect them from radiation damage. Without it, the neutrons would make the steel brittle. Secondly, to protect people against neutron and gamma ray emission, walls are constructed several meters thick of high-density concrete. A nuclear plant has similarities to a normal coal or oil-fired plant. The fission provides the heat to boil the water, and then steam drives turbines and generates electricity. To generate power, it is necessary to have a temperature difference. Just as important as a hot side is a cold side. So all power stations using steam are sited near a source of cooling water. However, it usually is illegal to warm a river because it will affect the environment. So after the cold water has condensed the steam, it must be cooled in cooling towers, ponds, or canals before being returned to rivers. Cooling towers are hollow inside. Water is sprayed into them while air is blown up. Some water evaporates, cooling the remainder. This way, the atmosphere absorbs the waste heat. The original design for the U.S. nuclear power stations was carried out by the Navy for use in submarines in the 50s. They adopted pure water, known as light water, as their moderator and coolant. To supply the extra neutrons to make up for those absorbed by the hydrogen, the fuel needs to be enriched to 2 to 3% uranium-235. This takes extra energy and cost. Canadian scientists wanted to avoid the expense of enriching uranium, so they used heavy water in their Canadian deuterium-uranium reactor, known as the CANDU. Heavy water is made with deuterium, which has the advantage of not absorbing neutrons, so natural, unenriched uranium can be used. The first Canadian nuclear power station started up at Chalk River in 1962. In Great Britain and France, high-pressure carbon dioxide was developed as the coolant. It could be heated to higher temperatures than water and was thus more efficient. The moderator was carbon. Fast breeder reactors are a new generation of reactors still being developed. In a reactor, uranium-238 can capture a fast neutron which turns into a proton, transmuting the uranium to neptunium, then plutonium. Plutonium is fissile like uranium, but needs fast neutrons. A fast breeder reactor uses plutonium as its fuel. Neutrons from the plutonium fission are captured by uranium-238, which is placed nearby. The uranium-238 is converted to more plutonium. It is called a fast breeder because it needs fast neutrons and because it breeds plutonium. Cooling is by molten sodium. Theoretically, Uranium in a breeder reactor should produce 60 times more energy than by passing it once through a standard reactor. However, the demonstration plants are not achieving this level of efficiency, and none is producing power commercially. This graph shows the binding energy per nucleon for different nuclei. That is the energy that would be released if the nuclei was made by adding protons and neutrons together. Hydrogen obviously has zero binding energy. If 2 deuterium nuclei were added together to make helium, a huge amount of energy would be released. Less energy would be produced in splitting uranium to, say, strontium or barium. The energies involved are millions of times greater than for chemical energy. To release energy, you have to work towards the maximum somewhere around iron. This giant machine is designed to heat and hold a very high temperature gas in imitation of the sun's processes. In a fusion reaction, energy is released when light atoms are fused together. The great lure of power from fusion is that the basic fuel is deuterium, a form of hydrogen. Deuterium can be extracted from water and is virtually inexhaustible. On the left is Culham Laboratory in the UK, where scientists have been working for 30 years towards the goal of power from fusion. Alongside is the JET Laboratory, where scientists and engineers from 14 European countries have built and are operating the world's largest nuclear fusion experiment. This torus is not designed to produce electricity. This is the smallest atom, hydrogen. Its nucleus is 1 proton, which is positively charged. It has 1 electron. However, the electrons don't play a direct role in nuclear reactions. This is an atom of deuterium, an isotope of hydrogen with a neutron in the nucleus. Deuterium occurs naturally in water and can be separated by hydrolysis. Tritium is another isotope of hydrogen, with 2 neutrons and 1 proton. Being extremely rare in nature, it would have to be made from neutron bombardment of lithium, or separated from heavy water in a heavy water-cooled reactor. The likeliest way to fusion power is to use the nuclei of these 2 atoms. But each nucleus has a positive electrical charge, so when they come close together, they repel each other. The only way to force them together is to make them collide at thousands of kilometers per second. To do this, they are heated to enormous temperatures, around 100 million degrees Celsius, 6 or 7 times hotter than the center of the sun. Well below that temperature, the particles are stripped of their electrons, which race around independently. This mixture of positive and negative particles is called a plasma. Some of the nuclei will collide and fuse together, forming a new single nucleus while ejecting a neutron. But how can this super-hot plasma be held together so the collisions can happen? If the plasma hits the walls of a container, it cools instantly. This loss of energy prevents fusion reactions happening. Magnetism can be used to hold the plasma because charged particles can be trapped in a magnetic field. Particles travel around the lines of magnetic force, so they are prevented from moving rapidly towards the walls. To stop the plasma escaping from the ends of the container, it is bent back on itself in a donut shape called a torus. The plasma is trapped in a ring with no ends from which to escape. The magnetic field confining the plasma inside the torus is produced by a series of coils. One of the main challenges so far has been to mold the magnetic field to the optimum shape. In a commercial reactor, the plasma will be wrapped in a blanket containing lithium, which absorbs the neutrons. Most of the energy being released from fusion reactions will be released as high-speed neutrons flying out of the plasma. These neutrons, traveling at thousands of kilometers a second, are slowed down by colliding with the lithium. The slowed-down neutrons react with lithium to produce tritium and helium. The tritium can then be used to fuel the reaction. The fuels for fusion will be deuterium and lithium. In slowing down the neutrons, the lithium becomes hot and will boil water to produce steam for power generation. This is Zeta, one of the earliest torus models. The results were published in 1958. Throughout the 1960s, scientists encountered instability problems while trying to control and heat plasmas to higher temperatures. The plasma would writhe and break away from the magnetic grip. But in 1968, the Russians reported a breakthrough with a torus of their own design called a tokamak. This tokamak could produce temperatures of 10 million degrees Celsius and could grip the plasma with fewer instabilities. Scientists in Europe and America converted to tokamaks. They could then reach 15 million degrees Celsius and hold that for 2/5 of a second. This is the Princeton Large Torus, which reached 82 million degrees Celsius in 1978. Gradually, the scientists were improving their grip on the plasma. Next, they needed to heat the plasma with more than their maximum of 250,000 amps. The joint European torus in the UK was built large enough to imitate conditions inside a commercial reactor. The large orange uprights being built here are the limbs of a large transformer. It will produce currents of up to 7 million amps to be passed through the plasma for initial heating. One of the principal magnetic fields used to grip the plasma is created by 32 of these giant copper coils. Each weighs 12 tons. Further shaping and positioning of the plasma is carried out by gigantic ring coils. The torus hull has concrete walls 2.8 meters thick to shield the operators from the high-speed neutrons. The doors weigh 400 tons each. The neutrons will make surrounding equipment radioactive, so it will need to be dismantled and disposed of. The volume of radioactive waste from a fusion power plant will be similar to a fission plant, but the radioactivity will be far less and will last a shorter time. In 1991, the Joint European Torus, or JET, produced for the first time ever nearly 2 megawatts of fusion power. In these experiments, a weak mixture of tritium was injected into a deuterium plasma and heated to 200 million degrees. In 1996, JET will carry out a series of tests with the correct fuel mix at full power. It is hoped that in the future, fusion power will be a solution to the environmental problems from coal, oil, and fission. In this section, we'll go back to fission and look at the reprocessing of uranium after it has been used. Once the fuel rods have been in use for 1.5 to 4 years, fission products gradually build up and absorb the neutrons, slowing down the reaction. The spent fuel assembly is lifted from the core through a channel to the spent fuel pool. 3 meters of water is enough to prevent radiation reaching the people above. It also provides cooling. Left on their own, the rods would heat up due to radioactive decay of the fission products. The original idea was that they would be stored here for about 5 years while most of the radiation died down. However, most power stations have nowhere to send their waste, and some have been storing rods underwater for up to 30 years. Some power stations store the spent fuel outside in special concrete containers, cooled by the air. The spent fuel contains 96% of the original uranium. This can be recovered and reused as fuel. There is also around 1% plutonium, another useful fuel. This leaves 3% waste to be disposed of. There is community suspicion over the reprocessing of fuel. In the past, there have been radioactive leaks, and there is worry that plutonium is used to make bombs. Canada and USA don't reprocess because it is cheaper to mine new uranium. Only Britain, France, Japan, and Sweden reprocess nuclear waste. One of the main reprocessing plants is at Sellafield in the United Kingdom. The fuel is transferred to a pool of water which cools the fuel and acts as a radiation barrier. The rods are chopped up and then dissolved in nitric acid. The uranium and plutonium are removed by an organic solvent. The byproducts need to be disposed of. Waste is classified into levels. In the UK, there are 3 levels: high, intermediate, and low-level waste. In USA, there is no intermediate classification. High-level waste is sometimes mixed with molten glass and stored on site until it cools down. The process is called vitrification. While they cool, they are stored in concrete vaults. The concrete is sometimes filled with iron shot, which is twice as dense as concrete. Much work is going on to test the disposal of high-level waste in deep underground stable rock formations. The radiation from the fuel rods won't be safe for nearby humans for 500 years. However, for thousands of years after that, it would be harmful if swallowed. Researchers are testing stable rock 500 to 1,000 meters underground. They are finding out if underground water will become contaminated and are checking the long-term effect of heat on the rock. The most acceptable method of disposal is underground in stable rock formations. In the UK, intermediate level waste includes the cladding stripped off the outside of the fuel rods. Usually it is encased in concrete inside stainless steel containers. These too await permanent storage. The world's first deep underground repository is at Forsmark in Sweden, under the sea. It is used for low-level and intermediate waste. Containers of waste are placed in position with this remotely controlled truck. When the containers are packed in, the vaults will be filled with concrete. Then a thick cap of concrete will cover the top. To prevent groundwater carrying away pollutants, many different barriers need to be built into the design. The challenge is to find areas with extremely slow water movement. Salt deposits were favored, but there is the danger that future volcanic activity may let in water. Low-level waste includes clothes and instruments that might have picked up some contamination. It is placed into drums of containers and disposed of in concrete-lined cells and covered over with earth and then replanted. Nuclear power costs about the same as other forms of fuel. It has the advantage of not producing smog or greenhouse warming. However, it produces radioactive waste that must be stored for generations after we have gone. Also, some poorly managed power stations have caused radioactive contamination. Commercial fusion power is unlikely before the year 2040. Current thinking is that it is far better to save energy than build new power stations. Nuclear power is only one of many energy options. We must look for ways to reduce our need for power and work out the most environmentally responsible methods of generating power.